Hello everyone, I'm Nannan Zhao. I will present DupHunter, a flexible high-performance deduplication framework for Docker registries. This work is done in collaboration with my fellow students, Hadeel, Subil, and Keren, and colleagues from IBM Research, Vasily, Dimitrios, Lukas, Anwar, and my advisor, Ali. Over the years, containers have become ubiquitous. We've seen their use in supporting from operating system deployment to the platform for big data analysis, running web servers, caches, and well as the new serverless paradigm. Containers are also seeing a lot of use in deep learning applications. Another way to look at the impact of container is that the market share they have gained recently. Containers already are a $2 billion market driven by large-scale containerization of existing business-critical applications. The trend is expected to grow at the rate of 30% per year, doubling by 2020. So containers are popular, and here to see this growth is reflected in the size of Docker image dataset. For example, if we go to Docker Hub webpage, we see that it stores about 3.6 million images repositories. Moreover, just in the last 10 months, this number has grown by 40%. All these images take a lot of storage space and cost. If left unchecked, this would not be sustainable. The research challenge here is that can we efficiently manage this big image dataset and do that without sacrificing performance? To this end, we've designed DupHunter, which is a deduplication technique for images in Docker registry. We made two important findings that drive our design. First, container images have been observed to have a lot of redundancy. For example, there is a significant amount of data that is duplicated across layers. Second, the way users access the registry is predictable. Thus, learning these access patterns can help us optimize the system. We use these two observations to design DupHunter, which does not only dedupe layers, but also reduces layer restore overhead. Our evaluation results show that in the highest data reduction mode, DupHunter can reduce storage space by up to 6.9 times. Similarly, in the highest performance mode, DupHunter can reduce the get layer latency by up to 2.8 times compared to the state of the art. Before I get into the details of DupHunter, let me give you a quick overview of Docker and Docker registry. Docker container is an executable package that includes all the required components for software deployment and provides isolation among containers. It's lightweight compared to virtual machine because all the containers running on the same server share the same kernel. Docker containers are created from Docker images. A Docker image contains a list of layers and an image manifest. Docker images are stored by Docker registries, such as Docker Hub, which enables easy deployment and faster distribution. Docker client can pull an image from Docker registry, run Docker image as a container instance, build a new image, and push the new image to Docker registry. One of the key observations we make is that there are significant redundant files in the image dataset. An early study by us has shown that 97% of the files across layers are duplicates. Removing such duplicates can save almost half of the space. However, existing techniques are unable to harness this redundancy. This is because each layer is already compressed in Docker registry image dataset. If we directly apply existing methods such as gdedup, vdedup, fs, dfs, and ceph on the compressed layer dataset. There's no space savings because compressed datasets are not deduplicate well. However, instead, if we decompress and unpack each layer and then apply different deduplication methods on the uncompressed layer dataset, we see that the existing method can significantly save storage space. For example, video can reduce space by up to 4 times. However, layer restore adds overhead on the get layer request. For example, layer restore incurs 98 times overhead for layer pulling request for ceph. Our second observation is that user access pattern is predictable. We observe that when a client pulls an image, it will first pull the manifest for the image, which contains a list of its containing layers. After that, the client will pull layers from the image, but not all the layers in the image will be pulled. To further understand the pulling pattern, we studied the IBM cloud registry workload that spans 7 available zones and the duration of 75 days. This graph shows the distribution of get layer request count for the same client. We see that the majority of layers are only fetched once by the same client. Next, we observe the client repulling pattern from the client side. This graph shows the CDF for client repull probability. Here, repull probability is the likelihood for user to repull an already stored layer, and it's calculated as the number of repulled layers divided by the number of total get layer requests issued by the same client. We see that half of the clients have a small repull probability of less than 0.2. This means that many clients only pull a layer once. We also observe that some clients have a very high repull probability. Moreover, we see that the slope of the CDFs is steep at both lower and higher probabilities, but become flat in the middle. This suggests that by tracking user access history, we can classify clients into 2 categories: always pull clients and pull once clients. When a get manifest request arrives, we can predict which layers in the image will be pulled. With the previous 2 observations in mind, we explore if we can predict a potential get layer request and pre-construct a layer upon receiving a get manifest request. For example, before the actual get layer request is even issued. Moreover, we want to know if there is enough time between a get manifest request and its subsequent get layer request to do a layer pre-construction. To answer this question, we analyze the inter-arrival time between a get manifest request and the subsequent get layer request. We see that the majority of the intervals are greater than 1 second. For example, 60% of the intervals from Sydney are greater than 5 seconds. So layer pre-construction is possible and can significantly reduce layer restore overhead. With these observations, let me now present the design of DupHunter. The main component of DupHunter are cluster of storage servers and a distributed metadata database. Docker client can communicate with the Docker DupHunter server using the registry API to upload and download layers. Each server in the cluster contains a backend storage system which stores layers and performs dedup. The duplication metadata is stored in the database. We use 3 techniques to reduce deduplication and restoring overhead in DupHunter, namely replica deduplication modes, parallel layer reconstruction, and preactive layer prefetching and preconstruction. DupHunter exploits existing replication approaches to improve performance. It supports two modes: basic deduplication modes, denoted as B mode N, which only keeps N-layer replicas intact, and dedupe the rest R-N layer replicas, where R is the layer replication level. It also supports a selective deduplication mode, denoted as S mode, which dedupe rare accessed layers more aggressively than popular ones. The goal here is to speed up accesses to popular layers and achieve higher storage savings. Here, the storage cluster is divided into a primary cluster consisting of P servers and a dedupe cluster consisting of D servers. P servers are responsible for storing full-layer tables, replicas, and the replicas of manifest, while D servers dedupe, store, and replica the unique files from the layer table. DupHunter introduces the concept of a layer slice, which is a collection of files on a single server belonging to the same layer. The slices are distributed evenly across the cluster. Using the slices allows DupHunter to rebuild a layer slice based on layer recipes in parallel and thereby improve layer reconstruction performance. To avoid the reconstruction latency during poolings, DupHunter employs a cache layer in both the primary and the dedupe cluster. DupHunter prefetch layer in the prefetch cache to avoid on-disk IOs on P servers. Additionally, to reduce layer restoring overhead, DupHunter preconstructs the layers and load them in preconstruct cache on disk and D servers. The user access history and image information are then saved in metadata database. To dedupe a layer, the layer is first decompressed into a layer archive file. Then DupHunter computes a file ID by hashing the file content and check if the ID is already present in the file index. If present, the file content is discarded. Otherwise, the file content will be saved as a unique file. Next, the unique file will be evenly distributed and replicated to different servers to make sure that the layer slices are similar sized. A slice recipe is also created, which contains the information for restoring a layer slice. After layer deduplication, a layer recipe is created for layer restoring. The use of slices and recipes makes the layer restoring process is straightforward. To restore a layer, we first rebuild the layer slices in parallel based on the slice recipes. Then we concatenate all layer slices together as a layer. To accurately predict the layers that will be accessed in the future, DupHunter keeps track of the image metadata and the user access patterns in two data structures. RL map maps an image to its containing layer set. UL map stores for each layer the layers the user has accessed and the corresponding pool count. When a get manifest request is received, DupHunter first calculates a set of image layers that have not been pulled by the user by calculating the difference between the image's layer set and the user's accessed layer set. The layers in the difference will be accessed soon. If the user is a repull user, DupHunter computes the subset of layers from the requested image that have already been pulled by the user. The users in the intersection will be pulled soon for this user. Next, we talk about how the get layer request is served in DupHunter. First, requests are passed through the tiers from top to the bottom. Upon get layer request, DupHunter first search the prefetch cache. If the layer is present, the request will be served from the cache. Otherwise, the request will be served from the layer store. If a get layer request cannot be served from the primary cluster due to a failure of the corresponding P servers, the request will be forwarded to the dup cluster. DupHunter will check whether the layer is in the stage area or the preconstruction cache. Otherwise, it will rebuild the layer. I have now described the design of DupHunter and its various techniques. Next, we evaluate its efficacy. We have evaluated the DupHunter using real-world traces from 4 IBM production registry clusters, Dallas, Frankfurt, London, and Sydney. Since there are no real layers in the traces, we downloaded around 1 TB of popular Docker images and matched the requested layers in IBM traces with real layers downloaded from Docker Hub to generate the workload. We evaluated 4 kinds of schemes. The first one is baseline scheme, which does not perform dedup. The second one is B mode n equals 1, 2, or 3, which means that n layer replicas are preserved and 3 minus n layer replicas are deduped. The third one is S mode, which means that the number of intact layer replicas is proportional to the layer's popularity. The last one is B mode 0, which dedupe all layer replicas. Here, we integrate B mode 0 with different dedupe methods and redundancy schemes, such as global file level deduplication on the replication, global block level deduplication under urea coding. We first look at DupHunter's end-to-end performance versus deduplication ratio for all the studied scenarios. We see that all four schemes, B mode 1, 2, and 3, and S mode, have a better get layer performance compared to baseline. Compared to the above 4 modes, B mode 0 has the highest dedupe ratio because all the layers are deduped. And we see the dedupe ratio decreases with the number of layer replicas preserved, while the performance improves. For B mode 0, we see that with the global file level deduplication is used, the dedupe ratio is increased to 2.1. When block level deduplication is used, the dedupe ratio increases to 3.0. Finally, the dedupe ratio increases to 6.9 if we use urea coding instead of replication. However, we note that the performance decreases with the dedupe ratio. Next, we look at the prefetch cache hit ratio. We compare DupHunter's prefetch algorithm with the state-of-the-art registry prefetch algorithm, LRU and ARC cache algorithm. We observe that DupHunter shows the highest hit ratio. For example, DupHunter's hit ratio for Sydney is 4.2 times higher than that of the state-of-the-art. Note that, as shown in the paper, the corresponding tail latency also improved by 13%. So DupHunter can provide higher hit ratio while reducing tail latency. Finally, we examine the preconstruction cache hit ratio. We see that the preconstruct cache hit ratio depends on the deduplication methods. As shown in this figure, global file level deduplication under replication has the highest hit ratio. Correspondingly, global file level deduplication under replication also has the lowest weight and miss ratio. This is because it has the lowest restoring latency, and majority of the layers can be pre-constructed on time. For more detailed analysis and results, I refer you to the paper. To conclude, I have presented the design and evaluation of DupHunter, which provides efficient deduplication for Docker registries. DupHunter exploits the redundancy in container images and predictable user access patterns to achieve high space savings with lower layer restore overhead. Our evaluation with real-world representative traces show that DupHunter reduces storage space usage by up to 6.9 times. It can also reduce the get layer latency up to 2.8 times compared to the state of the art. Finally, DupHunter is available at this link. Thank you for listening. If you have any questions, please feel free to contact me.